afternoon session, and the first talk by Sergey Sergeev on algebraic structures underlying the rational Kashiwara-Miwa type models.
Good afternoon, everyone. It's my pleasure to present something on such a meeting devoted to celebration of life and achievement of Rodney Baxter. By the way, yesterday during Mari's talk, I just realized that Mari forgot to mention two more people who are here in Australia following invitation of Rodney Baxter. It's Mengazeev and myself.
Yes.
They were all in the same cohort. Well, today I would like to report some essential achievement related to the unraveling of algebraic structure underlying the rational Kashiwara-Miwa model. And let me start with, well, introduction, which is historical introduction and some introductory point of view to all this stuff. A few years ago, in 2024, someone Bajanov, you know Bajanov, and myself, we found some interesting features of six-vertex model. Namely, we obtained what we called Ising type model formulation of the six-vertex model. Well, later, as a very occasional result, we obtained something which we called distant descendant of the six-vertex model, which is a rather interesting object from the algebraical point of view. So distant descendant, it's characterized by Q inside unit circle and also infinite number of spin states. Spin belongs to the set of the all real numbers, positive as well as negative. And it was quite unexpected in the theory of Ising type models with discrete spin. It was absolutely unexpected. And what happened from the algebraical point of view, it happens that proper representation of UQ of SL2, which serve such type of Ising type model, is in some sense a union of two other representations. So we call this phenomena introduction of half spins in the model. And at some stage, I'm not sure about Vladimir Bajanov, but myself, I understood that I understand nothing in the representation theory of all good UQ of SL2. Completely nothing. Something strange happened. Well, and this activity with revision of very old known technique in Young-Baxter theory, in L operators and so on, it requires some revision. And as the revision was done, in quite recent paper related to algebraic structures of Kashiwara-Miwa type model. It's not Kashiwara-Miwa model itself, it's Kashiwara-Miwa type model. Well, all this activity, of course, is related to Baxter's contribution to the field of interval systems. Namely, it's related to what we now call Baxter vectors. Baxter introduced his vectors when he studied 8-vertex model as some essential tool, but which allowed him to derive TQ equation. And later people understood that it's a very important object. And this object, Baxter vectors, they allow to establish relation between vertex type models. So it's here, it's like 6-vertex model in our particular case, and the whole class of interaction around phase type models. So later people understood that when you consider a pair of such Baxter vectors, which are denoted by dotted line here, and join them together. So then they can be seen as a particular internal structure of Lux operator for the same 6 vertex model. Lux operator for the 6 vertex model is just a way to describe UQ of SL2. And then next step is to look for a quantum intertwiner which intertwines such representation of such quantum spaces of L operators. Well, when we talk about Baxter vectors for 6 vertex model, it's important to mention that there are 2 types of Baxter vectors. Namely, when we try to solve such equation relating vertex, arithmetics, and interaction around phase type models, at some point you have choice, plus or minus. And this choice corresponds to what one can call type 1 Baxter vector and type 2 Baxter vectors. Well, type 1 Baxter vectors was used a lot. Disadvantage of type 1 is that interaction around phase models, it's just equivalent to initial 6 vertex model and therefore seems to be non-interesting. But later it appeared that an operator, well, according to Leningrad group, Fadeev-Takhtaljan papers, such an operator is called Sine-Gordon L operator, which gives evaluation representation of UQ of SL2 with the help of simple Weyl algebra. Well, it's just straightforward way to produce many other models related to statistical mechanics. The best example is chiral post model obtained in this way by Bazhanov and Stroganov. Also, using the same method, one can derive Fadeev-Volkov model, which is related to quantum dilogarithm and, to be precise, to modular double of quantum, and so on. And as well, references mentioned before, it's also case of type 1 Baxter vectors. And in addition to type 1 Baxter vectors, one can mention type 2, another choice of plus or minus sign somewhere. And type 2 Baxter vectors, they are, first of all, they have elliptic deformation to 8 vertex model and so on, and to Sklenin algebra from another side. So moreover, interaction around phase models related to the type 2, they are well known Andrews-Baxter-Forrester models, and I think here Pierce name is missed, since basic example is hard hexagon solved by Pierce and Baxter. Well, what about an operator appeared in this case? In trigonometric case, not an elliptic. I'm doing 6 vertex. Arithmetics as initial starting point. So they correspond to what is called Bose gas. It's a system also known for ages, I think from Middle Ages. It's a representation, evaluation representation of SL2 based on a single Q oscillator. Well, and in my brief message, I'll just remind you that when you start from such an operator, eventually you will produce rational Kashiwara-Miwa type model. And by the way, it's relatives, not only Kashiwara-Miwa type, but something else. Well, and now a little bit of technical details. First of all, we are talking about Q oscillator. So here on the top, you can see what I understand by algebra of Q oscillator. And this generalized algebra of Q oscillator, it involves 4 operators. E plus, E minus, creation and annihilation operator, usual one. And also 2 operators K and K prime. So they play a role of Q to power H or Q to power number of particles. While usual Q oscillator algebra here in the middle, That's just particular case of the algebraic buff. It's not something extraordinary, rather simple algebra. But what's interesting for this algebra? It's interesting that you can define homomorphism from a single copy of such algebra to a tensor product of two copies. Well, I asked artificial intelligence, Copilot and ChatGPT, do people know phenomenon of coproduct for Q-oscillator? ChatGPT told me no. It's something new, something strange, something unexpected. Well, coproduct has, of course, L-operator interpretation. Namely, if you start with type 2 Baxter vectors and construct L-operator will have such form as written at top. It's interesting to compare it with what is called Bose gas. On the right, you can see L-operator for the Bose gas, where lambda is spectral parameter. You can see when lambda stays on the diagonal and you consider product of L-operators, you obtain very well-defined quantum chain. Transfer matrix for quantum chain, which depends on L-operator in non-trivial way, and therefore it's suitable for construction of integrable models. But if you start with L-operator on the left and introduce lambda parameter, lambda will stay off diagonal, lambda power 1 in one place, lambda inverse in other place is just pure gauge. Therefore, such L-operator seem to be useless. But in a way, this useless L-operator defines coproduct and defines Kashiwara-Miwa type model at the end. So that's our hero, this L-operator. Coproduct corresponds to the product of L-operator, therefore coproduct is co-associative, which is good. Therefore, it's real coproduct. And then problem of construction of related models, this can be written as a middle line. We can take two representations of L-operator and try to intertwine them almost in the same way as we usually do in quantum algebraic approach. Well, and in what follows, one interesting thing to be mentioned is some particular representation of Q-oscillator. So we can call it evaluation representation. So this evaluation representation also follows straightforwardly from type 2 Baxter vectors. But this representation also appeared in completely different framework. Namely, many years ago, when same Bazhanov, same Mangazev like myself, we studied tetrahedron equation and we studied geometric approach to tetrahedron equation. We obtain evaluation representation of Q-oscillator explicitly in this form. And from the geometric point of view, operators U and V, they are just exponents of two angles of Ptolemei rectangular inscribed into circle. So therefore, this rather interesting representation. So later today, Kuniba, I think, he will discuss more simple representation of Q-oscillator, also with the help of simple Weyl algebra, which is also important in the theory. Well, since magic words coproduct was established, then some interesting question is we can talk about table of multiplication of different representations, how it works. Yes, indeed, it works. Here on top line, you can see just most simple examples how product of irreducible representations work. So, for instance, product of Fock times Fock, that can be decomposed into series of Fock representations, and multiplier here structure constant in some sense, is T. T is just unit circle. In a similar way, if one consider product of two anti-Fock space, difference between Fock and anti-Fock, Fock grows up, anti-Fock grows down with respect to annihilation and creation operators. Then you can see something similar. It's also infinite number of anti-Fock spaces, and structure constant is not just unit circle, but structure constant trivial, just direct sum of infinite number of anti-Fock spaces. And also, interesting thing to be mentioned, if one consider product of Fock and anti-Fock spaces, then the result can be decomposed into infinite number of finite dimensional spaces. Finite dimensional space, it's also representation space of Q-oscillator, but in such finite dimensional representations, operator K is not diagonal. It becomes a Jordan cell. Well, so since we have notion of coproduct, we can think about 3G symbols, or here they called Gordon coefficients or Wiener coefficients, doesn't matter. We can think about characters, and we can switch on the whole machinery of algebraic approach to how to construct intertwiner. Well, in particular, in all this business, at some stage, instead of Young-Buster equation, a star triangle equation will appear automatically for free. Well, on this slide, the key word is etc. What I mean by etc., it means that we have algebraic machine, standard usual algebraic machine, where we have inlet, and inlet is subject of representation. Please give particular representation. Then take this range, turn a few times, and as a result, you obtain integrable Ising type model. So that's how it works. Well, next, I think I'll skip most technical details and come to particular results that can be obtained in this way. So first of all, that's standard model that what we called rational Kashiwara-Miwa model. So why it's Kashiwara-Miwa? Because you can see on the top difference of spins, and here sum of spins. That's feature of Kashiwara-Miwa model. And also central spin somewhere defined as well. Well, if I'm not mistaken, technically this rational infinite dimensional Kashiwara-Miwa model first was obtained by, again, the same Bajanov and myself in the paper about various limits of master solution of the star triangle equation. Well, Kashiwara-Miwa model is subject of star triangle relation, and since we're doing some algebraic approach, it must be mentioned that such two spin weights, they naturally appear as a character. So in particular, this weight B is just spectral parameter x to the power log of k prime, but taken in certain particular presentation, which is related to particular homomorphism that I showed you before. And as a result, instead of inversion relation, standard inversion relation, we obtain this more general case, it's just summation formula. So in this summation formula, spectral parameter x is here, y is here, and their product is here. Property of character. But Kashiwara-Miwa model is not fundamental model in this approach. To obtain Kashiwara-Miwa model on this picture as a representation, you have to insert reducible representation, namely direct sum of two Fock space representations. Then machine is doing something, and as a result is rational Kashiwara-Miwa model. But if you insert a single irreducible Fock space representation, then as a result, you obtain something similar. Something similar where, look, we don't have indices of programmer anymore. We have indices inside programmer. Norm is Q square, indices are without square. So that phenomenon is the same happened in our previous paper about distant descendant of a 6-vertex model. So that's again the subject of star triangle equation. This weight is also subject of summation formula. It's as well character. So in this particular model, physical regime is Q must be negative, real negative. Negative Q is between 0 and 1. It's the same feature as in a distant descendant. And moreover, I don't know how to explain it. Partition function for this model is the same as before. Partition function coincides with partition function for 8-vertex model at free fermion point. That's observation that Bajan and myself did a few years ago, and truly speaking, we can't explain why it's so. Well, thus main result is reported. Thank you for your attention. Questions?
Yes, questions, please. So I have a question myself. The standard identity, you multiply two Q operators, which is realized with a few oscillator, and you'll get infinite sum of arbitrary spin representations. So is it type 1 or type 2?
Type 2.
Type
2. Type 2. Well, truly speaking, I expected question from Atsuo. What?
So you're talking about Kashiwara-Miwa model.
Yes.
And there is some non-relation model with Skrianian. So how is that story related to your?
So if you take modulo double of Skrianian algebra and do the same, almost the same, you obtain what we call master solution. And
modulo double representation.
Well, it's even before modulo double representation. Oops. So on this level, you take type 2 master vectors, but 8-vertex case.
Yeah.
And intertwine 8-vertex vector vectors, then you obtain standard Kashiwara-Miwa model, elliptic. And it was done in 80s. Stroganov showed me how to do it.
That was Japanese. Yeah.
But Stroganov showed me how to do it in one page.
Yamada.
Yeah.
So another question is, so that Kashiwara-Miwa and the relatives are the two-dimensional stuff line, version of Yambax. Do you know any 3D construction or reproduction of that solution using?
I expected this question. Well, from 3D case, coproducts, it simply corresponds to such combination of 3D ellipsorators. Blue and red lines, it's two-dimensional lines for this ellipsorator. I think you will use the same ellipsorator in your talk. Well, and when you combine them in such a way, you obtain co-product of two cooperators, of two Q-oscillators. But I simply, since we have very poor table of multiplication, I simply don't know how to use it in 3D. So maybe if in 3D we'll go to more complicated representations rather than simple Fock space, maybe something interesting will happen.
If there's no more question, let's thank the speaker.